Hey guys, hello everyone. Welcome to UNACADEMY once again, all of you guys. And in this video, we are going to learn a very simple and very important name reaction, Sharpless Epoxidation. So this reaction is studied under two categories, guys. One is the name reaction, absolutely, but the other one is asymmetric synthesis. All right. So it's a very important reaction for the asymmetric synthesis of a asymmetric synthesis of a chiral epoxide like this, right? So what are we going to study in this reaction is we will just try and understand the reaction and we will try to learn it with a simple trick so that in your examination you don't have to take a lot of time and find out the product, right? So it's a very simple reaction, guys. You see that the allylic alcohols are going to generate only the allylic alcohol specifically, yes. So they are going to generate the allylic epoxide in this way. Now the question is we need a enantiomeric epoxide, okay, in some enantiomeric excess. So what is this enantiomeric excess, guys? That is you have only one epoxide which is present in excess. Obviously there will be a little bit of impurity, but majorly you get one enantiomer, right? So how are we going to do that? And the question is which enantiomer is going to form? And the other question is what is going to happen to the rest of the molecule, right? So, yes, all of these questions I'm going to answer in this particular video, and we are also going to see some previous year questions which have been asked on Sharpless Epoxidation. So, guys, do subscribe to this channel if you already haven't. All right, so let's proceed. First thing I want to tell all of you about this reaction is that let's understand what are the prerequisites, what are the characteristics of this reaction, what is required. First, you require an oxygen source. So oxygen source is not usually taken to be H2O2 or OH minus, which we usually take, right, in the presence of a base formation of an epoxide of alpha beta unsaturated carbonyl. No, we take a tertiary butyl hydroperoxide over here. That has its own reasons. We are going to see it shortly. Tertiary butyl hydroperoxide, okay, and we are taking a catalyst, a Lewis acid, which is titanium, or let's say titanium isopropoxide like this, tetra isopropoxide like this, 10%. And the most important part, the star of this reaction is the chiral catalyst. Okay, so the chiral catalyst. How is the chiral catalyst being prepared? You have a chiral molecule. What is that molecule? Either you will be given DET, that is diethyl tartarate. See, look at this. DET is nothing, guys, tartaric acid ester salt, diethyl tartarate. Sometimes DIPT is also given. So just try to understand what is this. It is nothing diisopropyl tartarate. So tartaric acid is this particular acid. Okay, it's not a meso acid, guys. Just don't draw a sigma plane over here. No, it's chiral. So if you're taking ethyl, or if you're taking methyl, or if you're taking isopropyl, that doesn't matter. You just require the tartarate. Okay, so the ester could be anything, DET or DIPT. It is the plus or minus that is going to matter in the Sharpless epoxidation. Okay. Yes, you have a chiral catalyst formation, you have an oxygen source. Sometimes in your reaction, molecular sieves are also given. Molecular sieve with 4 angstrom as the, comma 4 angstrom is given. So what is this molecular sieve? It is to absorb moisture from the reaction. Okay, so moisture has to be eliminated from the reaction constantly, but you don't have to worry about this. Alright, it's not included in the reaction, right? Chalo. So what do you have to learn about the reaction is you have to learn a short trick. And what is the short trick, guys? That when you have plus DET, alright, so plus DET is RRDET form also. That is, if you find out the RNS configuration of the plus form, you will get RR on both of these carbons. Okay, so 1, 2, 3 is anti-clockwise, but since the least priority hydrogen is above the plane, so it is going to be R. So yeah, you can find it out. The plus DET group or the plus DIPT also for the same reason is going to be R and R. Alright. But experimentally it is found out to be levorotatory. Okay, so sorry, not levorotatory. This is the capital L, not the small l. Anyways, so when you're having the L plus DET, you will do the epoxidation. You will do the epoxidation on the re phase. What is the re phase and the psi phase? Very, very important. Guys, an alkene has two phases, or any planar molecule has two phases. Okay, one is above, one is below. Okay, the question is, in this alkene, phases are found out with respect to two carbons, that is with respect to this carbon and with respect to this carbon, right? So for the alkene, either it is a re-re phase or re-psi phase or psi-psi phase. Okay, but when I'm saying that I'm doing the epoxidation on the re phase, only one I'm mentioning, only one carbon I'm mentioning, that carbon is the one carbon which has the unsaturation alkene carbon only, but to which the allylic alcohol is connected. So to this carbon, we are going to find out the re or the psi phase, right? Chalo. So the LDET or plus DET or RRDET, okay, or RRDIPT in that case, all of these are going to give you refacial epoxidation, and the D or the minus DET or SSDET, all of these are the same molecule. Okay, so this set of molecule is the same, right, as you have seen over here. So if you're just taking the minus form, that will be SS, all right. So SSDET, right, that is going to give you the epoxidation on the psi phase. Okay, so let's figure it out, guys. So this is an experimental fact, right? We have just found this reaction experimentally giving you this product. So first, let's find out onto this carbon, what is the priority? So first priority always goes to the oxygen, second priority to this one, third priority to the hydrogen. So you see 1, 2, 3 is moving in the anti-clockwise direction. Okay, and we are looking at the molecule from the top. So we will say it is psi phase, but beware that psi is only the top phase. So psi from the top. Okay, so this particular alkene is psi from the top, and I am mentioning only one carbon of the alkene, that is the allylic alcohol carbon. Okay, this one, this particular one, right? It is psi from the top. So what happens is, you see the epoxidation is going to take place from below. Why? Because if it is psi top, then from the bottom it is going to be re. Yes, if from the side it is top, then bottom will be re, and we see the reagent. With respect to the reagent, the epoxidation is going to take place. So if it is plus DET, plus means refacial epoxidation. So re is the bottom face, and that is why the epoxide forms below the plane. This is 85% is 94% enantiomeric excess. So this is the short trick, guys. Now in your book, all right, in Claydon, how the example is given. Let's see what's happening, guys. This is the actual chiral catalyst, which is made of a combination of that titanium tetraisopropoxide Lewis acid, and along with that the L plus or minus DET. So this big one is a dimeric catalyst, chiral catalytic complex, to which the first of all the oxygen source is going to attach, and then the alkene is going to attach, so which is going to finally transfer the oxygen. You don't have to draw the whole thing, you just have to remember the trick, and this you can just avoid. Okay, it's not necessary that you remember this whole thing, not at all. In your CSIR examination, at least only the product will be asked. So yeah, no need. Okay, so let's just do first example, guys. June 2011. Very simple question, directly only Sharpless epoxidation. The major product formed in the following reaction is. So you are just going to try this and stop the video, and yeah, try it on your own. Now I'll tell you guys once again, which carbon you're going to find the re in the psi phase, the one which is an alkene carbon and also has the allylic alcohol connected. So this is the one. Give the priority order, one, always one to the allylic oxygen, second to this carbon, and third to the hydrogen. So 1, 2, 3 is psi phase. It is psi from the top. What is given? Tertiary butyl hydroperoxide is the oxygen source, and this is your combination chiral catalyst. So you are having plus diethyl tartarate. So you are having plus DET, which is going to be the RRDET, and also that is going to give you the rephase epoxidation. Alright, that will give the rephase epoxidation. So हमारे पास top में तो psi phase है guys. It is psi from the top. Then where are you going to get the epoxidation? Absolutely on the bottom. So allylic alcohol gets the epoxidation on the bottom face. This will be the answer. Here also you're getting bottom guys, but always remember Sharpless epoxidation only works for allylic alcohol. Okay, it does not work for a simple alkene. So C is absolutely wrong and D is also wrong. You are not getting the epoxide above based on this reagent. The answer is option number A. Alright, from June 2011. Now this question is so simple that sometimes or most of the times it is mixed with some other reaction because it is very simple. Right? Look at this, June 2012. Now guys, sharpless epoxidation is given and the only condition is L plus DET. Plus DET is given. Okay, but nothing else is given over here. So what are you going to do? The major product A and B formed in the following reaction sequence are. You are given an alkene tri-substituted. We don't have any use of this alkene, but you have a propargylic alcohol. So propargylic alcohol on reduction with lithium and in the presence of ethoxide base, you are going to get a trans-allylic alcohol. So A is going to be a trans-allylic alcohol. So this is not a trans allylic alcohol, it is rather a vinylic alcohol. So we are just going to click this option wrong. It is a cis allylic alcohol. We don't want this. We want a trans allylic alcohol. So guys, answer is option C because this is also cis once again. So wrong. Now let's say you have got the trans-allylic alcohol. You are going to once again find out the re-and phase of this particular carbon where there is allylic alcohol. Give the priority order 1, 2 and 3. So guys look at this. It is clockwise, which means we are having top. We are looking from the top. So top is a rephase. Top is a rephase. Now look at the reagent. Reagent is plus DET, which means RRDET, and that is going to give you refacial epoxidation. So refacial epoxidation will be above because above only we are having the top phase, right? So this is another very simple previous year question on the Sharpless epoxidation. Next, from June 2017. So absolutely guys, there are plenty of questions on Sharpless epoxidation. It's one of the easiest reactions, right? So yes, you will find out many reactions on this. The major product A and B formed in the following reaction sequence are. So once again, you have an allylic alcohol. This is the carbon to which you are going to find out the re and psi. Look at the reagent. Once again, tetraisopropoxide titanium. L plus DET gives you refacial epoxidation. Oxygen source. CH2Cl2 is just a solvent. Minus 20 degrees centigrade. Look at this. Molecular sieves 4 angstrom. That is just for absorption of moisture. Okay, everything sorted. Just find out the RNS. So first priority to this, second priority to the alkene carbon, third to the hydrogen. 1, 2, 3 is anti-clockwise, which means on the top you are having a psi phase. If it is a psi phase on the top, but we want the epoxidation on re, we are going to do it on the bottom. So option number A and option number C are correct. B and D are absolutely wrong. Okay, because we are going to have a epoxidation on below the plane, right? All right, very well. Now the next step is another name reaction that we have already done. It is the pane rearrangement. All right, it is already done, guys. You can just check out the video in the playlist. Pane rearrangement. What is that, guys? When you are having an epoxy alcohol. Look at this. Let's say it is some R group. It is your epoxy alcohol, and when you are having an OH like this, Alright, so what happens is in the presence of a base, it will become O minus. Alright, in the presence of a base, proton is removed, it will become O minus. It is going to do rearrangement. You're going to have a rearranged epoxide. The bond opens up O minus and you will have a rearranged epoxide. And since guys, it is the O minus is present within the molecule, it is doing an inversion attack. There is an inversion on this carbon, so it is going to be above like this. Be very careful about the stereochemistry. It is going to be above the plane because the ring opening requires opposite side attack. Okay, so this is the plane rearrangement. And if you just increase one more carbon from here, then you will not have the plane rearrangement because a four-membered oxytane ring is not going to form. Let's say I'm having something like this. So it is not going to attack over here and form a 1, 2, 3, 4 member ring. No, that is not plane rearrangement. Plane rearrangement is only when you are having a 3-member ring. All right. So very easy scoring topic, scoring reaction. You had the plane rearrangement very well. How would you know that you have the plane rearrangement? Because there is a possibility. Okay, so there is a possibility. Does it always take place? Absolutely. Now, all right, too many questions. Now, in the presence of a base, the nucleophile is deprotonated. Who is the nucleophile? This tertiary butyl sulfide. This is the nucleophile and it's also a bulky one, guys. So it is going to attack on this particular carbon. Always on the least hindered carbon, it's going to attack like this. And that is why this is your product. Okay. So the oxygen, yeah, this is actually above the plane. Why? Because the stereochemistry change does not happen on this carbon. So you're just going to get OH after protonation. So yes, guys, where is it? This one. See, these answers are such close that here you are getting the sulfide attack in between. That is not possible. Direct attack of sulfur is going to give you this reaction. Absolutely wrong. And in option number C, it is correct because first the rearrangement will take place and then the nucleophilic attack. So this is absolutely correct. Chain rearrangement and followed by the nucleophilic attack. So let's move onwards. Next good question, December 2017. The major product A and B in the following reaction sequence. So A and B. So what is mixed with the Sharpless epoxidation? The formation of an alkene. That is, first of all, in the presence of SiMe3 and OH, you are H2SO4 के presence में you are doing Peterson elimination. That is anti-elimination, anti-olefination. Why? Because when you are having the oxygen and silicon, depends on the reagents what will be the stereochemistry. If the reaction is in basic medium, you will have in the presence of an acid, OH is going to become OH2 positive and water, okay, not water, CbAF, that is a fluoride source. What is CbAF? All right, it is tetrabutyl ammonium salt of a fluoride. So now the fluoride F minus is free to attack over silicon and the bond opens up like this, right? So you're going to get a transallylic alcohol either in A or in B. C and D are absolutely wrong. You're not getting a cis alcohol, you will get a trans alcohol, transallylic alcohol. Be very, very careful about the stereochemistry. We did not have to change the molecule conformation because both of these were already trans or ये alkene भी trans. Alkane is also written in a zigzag way, so you're getting the trans alkene simply. Now moving onwards, you have the plus DET once again, right? So what are you just going to do? Find out the RS configuration. So 1, 2 and 3 is anti-clockwise. So the top phase is a psi phase once again and you are going to do the epoxidation on the re phase, which means once again below the plane. So the answer to this question is once again option A. You might be thinking that is the process correct because we are always doing below the plane epoxidation. But no guys, see what is happening in the previous years, maximum times the plus DET is used. That is going to give you refacial epoxidation, and this the same kind of alkene we are ending up with. That's why it is becoming the same all the time. Okay, but yes, the process is correct. Answer is A. Next is December 2018 question. Major products A and B in the following reaction sequence are. So, yes, guys, let's do this question very simple once again. And again, the same concept. You are given RDET, that is refacial epoxidation, all right, and you are given pane rearrangement for this. So, I just hope that you can do this in 2 seconds. All right, one, two, three. So, top is the side face, top side face, which means we are going to do bottom epoxidation. So A and C are absolutely wrong. We are doing the bottom face epoxidation. All right. Now, when you look at this molecule, you see that there is a possibility of pane rearrangement in the presence of a base NaOH. This is O minus attacks over here, causes inversion to happen. Yeah, look at this. Let's say I'm directly writing this OH, not O minus. Alright. Now where is the thiol going to attack? Or the thiophenolate ion, it is going to attack on the terminal end and it gives you this particular molecule. Alright. So very, very simple. Both of these are absolutely wrong. It could be something from below the plane, either B or D. In option number D, you have both of them on the same side and the sulfur will never attack on the more substituted or more hindered carbon. So absolutely wrong. B is the correct answer to this. Alright. So Sharpless epoxidation is guys very very simple, classified as a asymmetric reaction using the chiral catalyst, that is we are having DET and DIPT. So basically the tartrate unit and the tetra propoxide, isopropoxide titanium. These two units are combining to form a chiral reagent that gives you this following reaction. Okay, very very simple reaction guys. So for this question answer is B. Now once again guys, I'll see you all in another video, and till then guys, just keep practicing, keep attending the classes on Unacademy. Also guys, we are having a plenty of free sessions for discussion and question solving, so please also attend them. I'll see you all very soon. Bye everyone.